Welcome to our course on energy transition. Today we want to discuss geothermal energy use. First, let's see a small movie about it.
You may have relaxed in a natural hot springs pool, or seen the old faithful geyser blasting hot water into the air in Yellowstone National Park. But have you ever thought of where all that heat comes from? Well, it comes from deep beneath the surface of the Earth, and it's called geothermal energy. And we can use it to generate clean, renewable electricity. Okay, here's how geothermal works. Heat from the Earth's crust warms water that has seeped into underground reservoirs. In some places, when water becomes hot enough, it can break through the Earth's surface as steam or hot water. This usually happens where the Earth's crust, or plates, meet and shift. In the past, taking advantage of geothermal energy was limited to areas where hot water flowed near the surface. But as geothermal technologies advance, we can leverage even more of these natural, renewable energy sources. Engineers have developed a few different ways to produce power from geothermal wells drilled into the ground. Have a look at this. It's a dry steam geothermal power plant, and it's the most common type of geothermal technology used today. Underground steam flows directly to a turbine to drive a generator that produces electricity. Pretty straightforward. Another geothermal technology is called a flash steam power plant. A pump pushes hot fluid into a tank at the surface, where it cools. As it cools, the fluid flashes, or quickly turns into vapor. The vapor then drives a turbine and powers a generator. A binary cycle plant works differently. It uses two types of fluid. Hot fluid from underground heats a second fluid, called a heat transfer fluid, in a giant heat exchanger. The second fluid has a much lower boiling point than the first fluid, and so it flashes into vapor at a lower temperature. When the second fluid flashes, it spins a turbine that drives a generator. The environmental benefits of this clean, round-the-clock, renewable energy source are substantial. Low emissions, small physical footprint, and minimal environmental impact. The few byproducts that can come up are often re-injected underground. Geothermal energy can also help recycle wastewater. In California, wastewater from the city of Santa Rosa is injected into the ground to generate more geothermal energy. Some plants do produce solid waste, but that solid waste may contain minerals that we can remove and sell, which lowers the cost of this energy source. The U.S. Geological Survey estimates that untapped geothermal resources in the United States, if developed, could supply the equivalent of 10% of today's energy needs and cut our dependence on fossil fuels. In fact, electricity generated by geothermal energy already provides about 60% of the power along the Northern California coast, from the Golden Gate Bridge to the Oregon state line. Geothermal energy.
Our lecture will start as follows. We just will give an overview of geothermal use. We will discuss extracting geothermal energy. We will also see the environmental implication, economic consideration, and we will see some examples of geothermal installations. Where does the heat come from? So a lot of the Earth contains temperatures in excess of 5,000 degrees Celsius. Heat radial radiative decay of elements is the source for that. The heat energy continuously flows from the hot core. It's conductive heat flow, convective flows of molten mantle beneath the Earth's crust. The mean heat flux at the Earth's surface is 16 kilowatt of heat per square kilometer. It dissipates to the atmosphere and space later, tends to be strongest along tectonic plate boundaries. Volcanic activity transports hot materials to near the surface, only a small fraction of molten rock actually reaches the surface. Most of it is left at depth of 5 to 20 kilometers beneath the surface. Hydrological convection forms high-temperature geothermal systems at shallow depths of 500 to 3,000 meters. Here you see the Earth dynamics. So we have the hot core of the Earth. Via convection, the heat is transported to the surface and is most apparent at the tectonic boundaries, as you see here for the ridge here, and there it's easiest to extract geothermal energy. So here you see the temperature gradient. So the Earth is hottest at the inner core, as we already saw, in the vicinity of 5,000 degrees Celsius or about 5,000 Kelvin. Here you see the gradient. The temperature goes up in the inner core quite quickly, then it slows down a bit and then it speeds up again, and very close to the Earth's surface the gradient is quite big. We see this here now, so we have here the layers depth in meters. So this is just the upper crust, and we see here that the lower crust here has a gradient of 3 watts per meter per degree Kelvin or per degree Celsius. Then we have the next layer, which is in the vicinity of 1.5 per meter per Kelvin, and the uppest layer is 2.5 watt per meter per Celsius. Just imagine usually the unit is watt per square meter, but also we consider the depth, and therefore we come to watt per meter. So we have a geothermal site here. So you see the different forms, how the heat can come to the surface. So water can evaporate to steam, and you can have a well there, or it goes on its own via so-called fumarole, or if it's a mixture between water and steam, it's called a geyser. If it's only water, we may call it hot spring. The water comes in from a different site. You have to have impermeable crystal rocks, and the water flows here, and then it goes to the heat source and is then heated up or even evaporated. These are some examples of geyser. This is a geyser in Yellowstone National Park. This is Steamboat Springs. Some examples here from California and from New Zealand. And here you see along these tectonic plates, the geothermal energy could be extracted most easily. So here you see along the Rocky Mountains, and go to South America along the Andes, or in Europe, Iceland. So you see here the American plate is hitting the European plate, but also along the Mediterranean Sea, along the Nile, and here especially in the Pacific, along Japan, Philippines, Indonesia, and New Zealand. Here you see the direction of the movements and the effect at the borders here. Just you see that the Pacific plate is moving towards northwest. Let's talk about the methods of heat destruction. Most simplest is borehole heat exchanger. So you just extract the heat from a rock formation. Then you have hydrothermal systems where you extract the water from existing thermal groundwater. And then you have hot dry rock. So you artificially pump in cold water, which is getting heated up, and you take off the hot water. Here you see the typical temperature. So in this vicinity, it's just the heat extraction via heat pumps. Then you just, if you go deeper, then you have the use of hydrothermal systems. You don't need any heat pumps anymore, and temperature may go up to 100 degrees. If you have a higher temperature and you go very deep, you can use the hot dry rock, and then you extract even process heat and generate power. If we talk about geothermal energy, just it's quite important we discuss about some units relevant for that. So we have pressure. The official unit is Pascal. It's Newton per square meter. Often you find the unit 100 kilopascal. It's equivalent to 1 atmosphere, a unit which has been formerly used, or 1 bar. And Often in North America you use the unit PSI, so that's equivalent to 14.5 PSI, or 1 megapascal is about 10 atmosphere. This is 145 PSI. Temperature, SI units, it's Kelvin. Often Celsius is used. This is equidistant. More difficult it gets with Fahrenheit. So 0 degrees Celsius is equivalent to 32 degrees Fahrenheit, or 273, exactly 0.15 Kelvin. But it's sufficient if you use 273 Kelvin. 100 degrees Celsius is equivalent to 212 degrees Fahrenheit, or 373 Kelvin. Just let's take a look at the different ground structure. So you have structures with high porosity. So for example, grounded grains, uniform size. Then you have formations with low porosity. This may consist also of grounded grains, but there are many sites, so there's no sorting and the porosity is reduced. Then you have medium porosity, so you have angular grains, uniform size, a kind of good sorting, and water can go through those. Then you have very low porosity, so these are angular grains, many sizes, but pure sorting. Then you have also, if you take a look, vesicular porosity, so they may not be interconnected, for example, basalt, so there's no way water can flow through. You have solution porosity, so mid-solution along the crystal boundaries, for example at limestone, or porosity along the fractures or bending planes. So of the porosity versus hydraulic conductivity, so you have here, for example, clay porosity is medium, the hydraulic conductivity is very poor, so you have less than 10 to a power of -2. Salt, it's equivalent, it's similar in porosity, but the hydraulic conductivity can be a bit higher. You have sand, volcanic ash, so with lower porosity, but hydraulic conductivity can be significantly higher, or gravel, which has a lower porosity but very high hydraulic conductivity. Mud rock, sandstone, and so on. You see here these numbers, so they have very much reduced hydraulic conductivity. Depends on the local condition. Sometimes they may go up in the case of sandstone or limestone. Crystalline rock, so we have, for example, solidified lava, porosity very poor, and the hydraulic conductivity could be from very poor to good. Granite, you have here very low porosity, and the hydraulic conductivity is really poor. And slate, same, you have a low porosity but really poor hydraulic conductivity. Let's talk about the hot dry rock schematic. So this, in very simple words, you drill 2 holes, 2 wells. The rock between the wells have to be fractures, and there has to be hydraulic conductivity, so the cold water can flow to the extraction well, and hot water is pumped up on the second well. It depends on the local conditions, so you have to find out which material is down there. So here is hot dry rock technology, also another scheme of that and a photo. So some data. So wells are usually drilled 3 to 6 kilometers into the crust, reaching hot crystalline formations there. Water is pumped into the rock formations. The water flows through natural fissures, picking up heat, and hot water or even steam returns to the surface. And the steam is used to generate power. You can even create more steam with a flash measure. We'll explain a bit later. By the way, it's not as in the film, it's due to the cooling that more steam is generated. It's due to the reduction of pressure. And the reduction of pressure lowers the boiling point, and therefore more steam is created. Here we have the hot fractured rock. So you have to have fractured rock in order to have sufficient hydraulic conductivity. You see some typical distances here. Here the temperature is 200 degrees Celsius. The distance between the producing well and the injecting well is 600 meters. And the production is about 50 kilograms per second of steam. Here, in order to explore such potential, you have to use a so-called geophone. You have a sound source, and if you listen to it by the response of the rock formation, you can say whether it's porous, whether it's hydraulic, conductible, and so on. And this shows here relatively small power, 1.5 up to 4.5 megawatt. Some target parameters of a 2-well high-dry rock system. So you have a flow rate in the vicinity of 72 to 100 kilograms per second. You have an effective heat exchange area of more than 2 million square meters. That's about 2 square kilometers. You have an accessible rock volume of more than 2 by 0.2 billion cubic meters. And the impedance is 0.1 megapascal per liter per second. And the water loss is less than 10%. So 1 cubic meter of hot dry rock has an energy content of 70,000 tons of coal. Just if you extract energy, that cools the hot dry rock formation only by 1 degree. Between 19 and 138 gigawatts power potential usable at existing geothermal sites. So the performance versus rock type. So you have here hard rock, so the thermal conductivity is quite good, and you have a extraction rate of watt per meter of maximum 80, means you have an energy yield per meters of borehole of 135 kilowatt hours per meter per year. At unconsolidated rock, which is saturated, you have an extraction rate of 45 to 50 watt per meter and an energy per meter of borehole of 100 kilowatt hours per meter per year. And unconsolidated dry rock, you have a thermal conductibility of 1.5 watt per meter Kelvin, and you have a specific extraction rate of 30 watt per meter, or an energy yield of the borehole of 65 kilowatt hours per meter per year. So you have some examples here from different deep wells exploration holes, different temperature. Here you see a difference between the bottom temperature and the upper temperature. This could be quite different, depends on the depth, on the insulation and the rock formation and so on. Dry steam is extracted from the natural reservoir, so the temperature in the vicinity of 180 to 225 degrees Celsius. The pressure is 4 to 8 megapascal and the velocity is 200 or even more kilometers an hour. The steam is used to drive a turbo generator, and the steam is condensed and pumped back into the ground. Can achieve about 1 kilowatt hour of electricity per 6.5 kilograms of steam. Or in other words, a 55 megawatt plant needs about 100 kilograms per second of steam. Here you have the schematic here. So you have the production well from the geothermal zone. You have then the turbine and the generator. There is still steam. In order to be pumped back, you have to cool it down. You have the condenser here, and then the steam is transformed into liquid, and this condensate can be pumped back into the ground via an injection well. Here's a cooling power, so you suck air and cool down, and then you have this typical air and water vapor above the power plant. So now we come to the flash process. So you have a mixture between steam and water, which you extract from the ground. The pressure of this mixture drops at the surface, so artificially lower the pressure, and then you reduce the boiling point and more water is transformed into steam. Then you separate the steam from the water, and the steam is able to drive the turbine. Turbine drives an electrical generator in the vicinity of 5 to 100 megawatts, uses about typically 6 to 9 tons of steam per hour. So here you see a single flash steam power plant. So you have here the geothermal reservoir. Then you have a mixture between steam and water. Here the pressure is reduced in the yellow part. You create more steam out of the hot water, and then you feed the turbine, as you saw before, which feeds a generator. You cool it down and inject back the condensate to the injection well. Or if you have the possibility, you can supply heat to direct heat users. You can also use a double flash, which has a higher efficiency, but the procedure is similar to single flash operation. So you still use the unflashed liquid in an even more low pressure tank, and then the rest flashes also, or some of the rest flashes also to steam. The steam drives a second stage turbine. To drive the second turbine, you may also use hot exhaust from the first turbine. This increases output by about 20 to 25% at only a 5% cost increase of the power plant. You see that? So this is pretty similar, just the pressure here at the second stage is even lower than at the first stage, and you may even use here heat from the condensate. Then are so-called binary cycle power plants. So they work at temperature between 100 and 150 degrees Celsius. They use organic liquid, which has a low boiling temperature, and they vaporize it. For example, isobutane, isopentane. And then you can create vapor at lower temperatures, and you use that vapor to drive a turbine. Then you cause the vapor to condensate, and you recycle that vapor. So efficiency is relatively low, only 7 to 12%. This is due to the Carnot efficiency, because the temperature difference is really low. So even the best theoretical efficiency as the Carnot efficiency is quite low. Power plant in the vicinity of 0.1 to 40 megawatts are quite common. You see here, so here you need a heat exchanger because you cannot use the organic liquid directly, because it will poison the environment and also is quite expensive. So here you have a heat exchanger, just use the heat. You have the organic vapor which evaporates at quite low temperature, and by this steam you drive the turbine and again a generator, and you recycle it by condensing it. Can even do a more advanced if you use two media which evaporate at different temperatures. So you see the influence of temperature. So you see here the power production at 100 degrees Celsius only is quite low, so it's below 1 megawatt. If you achieve higher temperature, if you go to the extreme 190 or even 220 degrees Celsius, you see that at the same flow, for example here 100 kilograms per second, you may achieve 10 megawatts. By doubling the temperature, or a bit more than doubling, you achieve more than 10 times the power output at this power plant, not in general. So here you see the Kalina process. This was developed by Dr. Kalina, and there you have liquid with several boiling points. So you have even an increased conversion efficiency. Here you see a small movie about that.
In today's video, we will understand how does a Kalina cycle power plant work. Here we will mainly investigate what's the reason behind its high thermal efficiency compared to the conventional power plant cycles. So let's start. The major difference between a conventional cycle and a Kalina cycle is that Kalina cycles use mixture of two fluids as working fluid. And most commonly used working fluid in a Kalina cycle is mixture of water and ammonia. So what's the advantage of this? Why should we use a mixer as a working fluid? To get answer for this question, let's see temperature entropy diagram of a conventional cycle and a Kalina cycle. Here it is. The first one is a TS diagram for a conventional Rankine cycle, and this is TS diagram for a Kalina cycle. So here you can notice a major difference between these two. In a Rankine cycle, during phase transformation, temperature doesn't change, it remains same. You can say during heat addition process 2 to 3, temperature doesn't increase during phase transformation. Similarly, again in condenser, the process 4 to 1, the temperature doesn't change due to phase change. But this is not the case with the Kalina cycle. Here even during phase change temperature changes. You can see it over here. During heat addition temperature rises and during heat rejection temperature drops, since we are using a mixture as a working fluid. And this small deviation in thermal cycle makes all the difference in Kalina cycle. This will explain why Kalina cycle has got much higher thermal efficiency compared to a Rankine cycle. Simply because of this reason. Efficiency of a Carnot engine can increase due to two reasons. First, when temperature at heat rejection side decrease, or when temperature at heat absorption side increase. So in order to use this formula, we will take average heat addition temperature and average heat rejection temperature for both the cycles. For a Rankine cycle, average heat rejection and average heat addition temperature will be like this. Average heat rejection temperature is same as the condenser temperature because temperature is uniform during the process. And roughly this will be average heat rejection temperature. And these two average values for a Kalina cycle will be like this. You can see it's much wider compared to a Rankine cycle. It has got higher average heat absorption temperature and a lower average heat rejection temperature. So obviously it will have a high thermal efficiency. Now let's see how this cycle is implemented in actual case. How does it work practically? First we will start with a very simplified Kalina cycle power plant. It has got four major components as a Rankine cycle: a steam turbine, a condenser, a compressor, and a boiler. When mixture expands through the turbine, power is generated over here. But the main difficulty in a Kalina cycle is over here, at condenser. Because right after the turbine, the working fluid will have almost 70% of ammonia by weight. Now, according to the phase diagram, when concentration of ammonia is high, the condensing temperature is very low. You can see it here. When concentration of ammonia is 70%, the condensing temperature is really low. If you want to condense such a fluid, you have to supply a very low temperature coolant through the condenser. That is not practical anyway. So what we will do, we will alter this concentration. We will try to decrease concentration of this ammonia with help of a device called separator. What this separator will do, it will separate out the working fluid to a lean mixture and a rich mixture. And this lean mixture, which is having almost 30% of ammonia by weight, will mix with the exit fluid at the steam turbine and it will produce a mixture of almost 40% of ammonia by concentration. Now if you check at phase diagram, such a mixture will have much higher condensing temperature, almost over here. This can be condensed using a regular cooling water supply. Now the condensation process is over, but we have to regain the original ammonia concentration in other parts of the cycle. For that purpose, rich mixture from separator will get mixed with the incoming stream and the working fluid will regain its original concentration, the 70% of concentration. If you check temperature entropy diagram of a Kalina cycle carefully, you can notice one thing over there. Temperature at exit of steam turbine is much higher than temperature at inlet of condenser. Or temperature at point 4 is much higher than temperature at point 2. You can see it over here. But this was not the case of the Rankine cycle. In Rankine cycle, these temperature levels were in other way. Temperature at point 4 was lower than temperature at point 2. After this point 4, we are rejecting heat to the surrounding. And after this point 2, we are absorbing heat from some external agency. So why can't we supply some amount of heat from point 4 to point 2, which will save some energy and will obviously increase the power plant efficiency. That's exactly what we do here. We are introducing a heat exchanger called recuperator. And function of recuperator is to transfer some amount of heat from point 4 to point 2. This is obviously possible because temperature at point 4 is higher than temperature at point 2. And thanks to the recuperator, you need not to supply same amount of heat input you supplied before. So recuperator heat transfer increases thermal efficiency of a Kalina cycle to a much higher level. And all these things prove that Kalina cycle is the power plant technology of the future. Thank you for watching the video. Have a nice day.
So here we see a comparison of the conversion efficiency of the different methods. On top we see the theoretical Carnot efficiency, which shows the maximum possible efficiency. This is all for ambient temperature of 40 degrees Celsius. Below we have the process temperature. So you see here, for temperature of 40 degrees, the temperature difference is 0 and therefore the efficiency is 0. So if we go up, for example, to 140 degrees, so we would have a temperature difference of 100 degrees for the Carnot efficiency. It would be in the vicinity of 24% of possible conversion efficiency. The best available efficiency is the one from the Kalina process. So we see here we will be in the vicinity of 12%. The open Rankine cycle is in the same vicinity, also in the vicinity of a little bit above 10%, 12%, and 11%. If we go to the flash process, they need a certain minimum temperature which is above the 140 degrees. So here for the single flash process, for example, for 160 degrees, we have an efficiency of 7%. For double flash process, a little bit above that. If you go to higher temperature, this difference may increase. Let's talk about combined cycle plants. This is a combination of a conventional steam turbine and a binary cycle technology. So we have the steam, which drives a primary turbine. We have the remaining heat used to create organic vapor. We have the organic vapor, which drives a second turbine. Plant sizes are in the vicinity of 10 to 100 megawatt or more. Significantly greater efficiencies. We have a higher overall utilization, and we can extract more power and heat from a geothermal resource. The direct use of geothermal heat, we also can use the geothermal heat directly rather than for power generation. You can extract the heat from low temperature resources also, which are below 150 degrees Celsius. And the applications have to be near the source, so less than 10 kilometers. Otherwise, it doesn't make sense to transport the direct heat. You see some heat pumps. So you see here the depth and the achievable temperature and the seasonal variation. You see if you are at low depth, there is some seasonal variation. The deeper you go, the less seasonal variation you have. Here you see a geothermal district heating. So you have here the cycle via a heat exchanger, and instead of heating the ambient via a cooling tower, you use the heat for domestic heat here. Here you see some examples for Southampton, how the pipe has to be made in order to supply heat to a village here. The technological issues are that geothermal fluids may be corrosive. They contain gases such as hydrogen sulfide, corrosion. Also, the scaling up is problematic because you sometimes only have a limited area where you can extract geothermal energy from. It requires careful selection of materials and diligent operating procedures. A typical capacity factor is 85 to 95%. If you compare that, for example, to solar or wind power, this is really high. Some technologies, the achievable temperature and the use. So if you have a high temperature reservoir which is above 220 degrees Celsius, you have as a reservoir fluid, you can use either water or steam. You can use it for power generation. Can often a technology, as we saw in the graph before, you can have a flash steam process or combined flash and binary cycles. You also may use that directly via heat exchanger or heat pumps. If you have intermediate temperatures of 100 to 220 degrees Celsius, the reservoir fluid is usually water. You can use it also for power generation, but also for direct use. So for binary cycle, direct fluid use, also heat exchangers or heat pumps. For low temperatures, so means between 150 degrees Celsius, you only have water and you only can use it directly. So you can use directly the fluid or via heat exchanger. Here are some examples here from 1999, a 60 megawatt power plant in Italy. So the maximum load is 55 megawatts for that. The annual produced electricity is 462.845 gigawatt hours of operation. of the plant is 8,748. That means you have very high load factor or capacity factor of 96.1%. And availability factor, so availability where you could theoretically use the power plant. Sometimes you don't need energy. And this was up to 99.9%. Also, you have to consider environmental impacts. You have some vegetation loss, you have soil erosion, landslide sometimes, the air. So they have a slight air heating, you have local fogging ground. So you have the reservoir cooling. And sometimes you have tremors. It's already usually in a region where you have seismic activities, but this may increase to geothermal use. The water, you have a watershed impact. You have damming steams. You have sometimes hydrothermal eruptions. You have low water table, subsidence, some noise, but only close to the plant. So it's quite environmental friendly. Is it really renewable? So actually we deplete heat and the ground cools. It's not steady state in a very large scale. So the Earth's core does not replenish heat to crust quickly enough. For example, Iceland's geothermal energy could provide 1,700 megawatts for 100 years. Presently only 780 megawatts are used of that. The cost factor, so this is the temperature and the depth of the resource. The type of resource, whether it's steam, a liquid or mix. The availability volume of resource. The chemistry of the resource. The permeability of the rock formation, as we saw before. The size and technology of the power plant. And the infrastructure, so road, transmission lines and so on. So let's see some costs. So in general, we have to say it's highly variable by the site. So there are many cost factors. Also, you have high exploration costs. So you need high initial capital, but then you have low operating costs because the fuel is free. Significant exploration and operation risks adds to overall capital costs depending on interest rate. Also a risk premium for that, which increases further interest rates. So here you see a development of the cost spent. So the beginning already you spent just for reconnaissance and before the exploration and geochemical starts is about $1 million. It's a logarithmic scale here. So here next step is already $2 million. Then you have the exploration drilling. Then you already spent $10 million. And then you have a really solid business plan only. So here you see the money spent. So for high discharge wells, for 15 megawatts per well, most of the costs are the power plant. If you go to low discharge wells, 5 megawatts, so you have the steam collection system, almost takes as much money as the power plant. The costs of water and steam. So for high temperature, usually costs are in the vicinity of 3.5 to 6 US dollar per ton of steam. For medium temperature, it's about 3 to 4.5 US dollar per ton. If you go to lower temperatures, not steam anymore, it's hot water. So this is for medium temperature, 2 to 4 dollar per ton of hot water. For low temperature is only $1 to $2 per hot water. To give you comparing examples, in Germany, the household heating costs are in the vicinity of 5 cents per kilowatt hour. So you will have about 3.4 euro to heat up 1 ton or 1,000 liters of hot water from 20 degrees to 80 degrees. So the costs of the per kilowatt hour of electricity being generated for small plants with a high quality resource, it's between 5 and 7 cents per kilowatt hour. If you have large plant, you may halve this cost down to 2.5 cents per kilowatt hour. Medium plants, it's 4 to 6 cents per kilowatt hour. If you have a medium quality resource only, costs increase So even at large plants, they will go up to 4 to 6 cents per kilowatt hour. And low quality resource may only have small local plants which can offer electricity in the vicinity to 6 to 10.5 cents per kilowatt hour. If you remember this number we got from photovoltaics, they are already significantly lower, but you have to consider the high availability and the high capacity factor of geothermal energy. So here are some examples of direct capital costs, what you spend for exploration per kilowatt of installed capacity. Remember, just a photovoltaic power plant is nowadays in the vicinity of about 1,000 euro per or $1,000 per kilowatt. And here you spend significantly more, but you have this high availability and the high capacity factor. The indirect costs, so sometimes the locations are quite far away from cities and so on, and therefore you have to check the availability of skilled labor on site, the infrastructure and access, the political stability, so indirect costs, which are in the vicinity of 5 to 10% of the direct costs, are fair. It's about 10 to 60, 30% of the direct costs, or poor would be 30 to 60% of the direct costs. Operation and maintenance costs. So the steam fields, you have costs per kilowatt hour in the vicinity of 0.35 to 0.7 US dollar per kilowatt hour. For small plants, for larger plants, this is less than half, so it's only 0.15 to 0.25 cents per kilowatt hour. For the power plant also you have a reduction if you go to larger plants. So you have maintenance costs in the vicinity of 0.45 to 0.7 US dollar per kilowatt hour. If you have large power plants, its maintenance and the operation maintenance costs are in the vicinity of 0.25 to 0.45 dollar cents per kilowatt hour. So in total, this is relatively small compared to other power plants, below 1 cent per kilowatt hour. Another movie.
Sulfur, it's really hot, it's really steamy. Geothermal in action. Geothermal instability creates large and impressive hot springs all over Iceland. Here we are enjoying one of the most famous, the Blue Lagoon in Reykjavik, the capital. Iceland, we're at what's called the Blue Lagoon, and it's famous for being these amazing hot springs where people are allowed to swim in, but that's not the main purpose. Is actually the hot water is a byproduct from a power plant you see behind me. And the unique thing is the scientists have figured out by studying geology that there are pockets of hot water trapped below the earth. They're being heated by liquid hot magma, and what they've done, the engineers have figured out how to bring that water up to the surface in order to make electricity. So 99% of Iceland's electricity comes from these geothermal power plants. And on top of that, it makes a pretty cool place to come and enjoy the amazing hot healing waters of a hot spring. The first step in making electricity in a geothermal power plant is to drill a hole down to where the superheated water is. Step 2 is to bring that hot water up and let it release as steam. The steam then turns a turbine, and you can see in step 3 that turbine will spin a magnet in a generator, making an electrical current. That electricity can then be put on the grid and brought to people's houses and businesses and schools. The water can then head to a cooling tower where it can cool down and then be either pumped back into the earth via the injection well in step 5, or in the case of the Blue Lagoon, pumped out into a giant swimming pool for all to enjoy. So geothermal electrical energy production probably isn't for everyone in every situation. However, if you have access to extremely hot water heated by the earth, it's an absolutely amazing and clean source of renewable energy. There is another way to capture energy from the earth, and that's what we'll be looking at next. It's known as a geothermal heat pump. Heat pump. Water or a refrigerant moves through a loop of pipes. When the weather is cold, the water or refrigerant heats up as it travels through the part of the loop that's buried underground. Once it gets back above ground, the warmed water or refrigerant transfers heat into the building. The water or refrigerant cools down after its heat is transferred. It is then pumped back underground where it heats up once more, starting the process again. On a hot day, the system can run in reverse. The water or refrigerant cools the building and then is pumped underground where extra heat is transferred to the ground around the pipes. The great thing about geothermal heat pumps as opposed to a geothermal power plant is you don't need to be near liquid hot magma or a geothermal hotspot. Anybody could install one of these and save an enormous amount of energy and money heating and cooling their home.
So we see here some examples of some countries which offer a geothermal resource. In general, if you see the total numbers, this is not very much compared to other renewable energy resources because the resources are quite limited to some specific regions. So the world production is about 67 terawatt hours. Full load hours are really good, so on average 6,276 full load hours. So compare it to a photovoltaic power plant, Germany, which offers only about 1,000 full load hours. The largest geothermal power station is now in Iceland. the Helles Haiti with a power of 303 megawatts. The next one is in Philippines, in Malitbok with a power of 233 megawatts. Then the next in Indonesia, 227 megawatts. Mexico, there are two equal ones with 220 megawatts. Other attractive sites are the Rift region in Kenya, but also in Italy, France, New Zealand, Nicaragua, Russia, and Japan. Here's a Geysir power plant. Here the one we saw, the Blue Lagoon power plant south of Reykjavik in Iceland. So it provides 76.5 megawatts in electric power plus 150 megawatts for thermal use. We saw there are bigger power plants in Iceland. The well testing in Guatemala. You see that the cost decreased, but not as much as other renewables. So from 1981, about 3,000 capital costs per kilowatt. And the overall costs in electricity production have been in the vicinity of 8.5 cents per kilowatt hour. 10 years later, it was 2,600 per capacity, and operation costs had been 5.7 cents per kilowatt hour. This is now some time ago, but these costs didn't change a lot. Here we see the top 10 geothermal power use. So we have the United States, which generated about 15 terawatt hours of geothermal electricity, followed by the Philippines with about 11 terawatt hours of geothermal power, Indonesia 10 terawatt hours of geothermal power, New Zealand 7.4 terawatt hours, and so on. You see Iceland is here with 5 terawatt hours. As a summary, geothermal power as a renewable energy source is environmentally very attractive, but only a source at certain locations. It's likely to remain an adjunct power to other energy sources, a part of the portfolio of energy technologies. Exploration risk and upfront capital costs remain a barrier. That's it. Now we just discuss about some exercise to do this. So first part is a geothermal well has been discovered. At the source it offers a temperature of 80 degrees Celsius at a flux of 10 liters per second. For a district heating space, an insulated pipeline to the houses has been built. At the houses, the temperature is still at 65 degrees Celsius, same flux. Water and house temperature without the heating would be at 10 degrees Celsius. First question is, how much energy is lost in the pipe during 1 year? How much energy can be saved in the households during 1 year by substituting a share of the original gas heating? We consider the efficiency of the gas heater or the stove of 80%. How much CO2 emissions can be avoided during 1 year? What data we need for that problem? Try to find them in the physical tables. I give some of them. So the heat capacity or the specific heat of water is 4.185 joule per Kelvin per gram. The heating value of natural gas, you get 50 megajoule out of 1 kilogram of natural gas. Just have to consider the 80% of conversion efficiency to heat for the heater. And the natural gas emits 56.1 kilogram of carbon dioxide per gigajoule of heat energy. And the density of water is 1000 kilograms per cubic meter. Next part is a converter directly at the source is featuring a Kalina process. So we have two different media with a low boiling temperature and is offering a conversion efficiency which is about 2/3 of the equivalent Carnot efficiency. So remember, Carnot efficiency is 1 minus the lower temperature divided by the high temperature. So the low temperature is the ambient, for example 10 degrees, and the high temperature. How much is the actual total efficiency considering an electrical generator with efficiency of 90%? How much electrical energy can be generated during 1 year? How much are the maximum investment costs to make it profitable, considering 30 years of lifetime and an electricity value of 0.1 euro per kilowatt hour at 0% interest rates, zero gain? So this is just, we want to find the limit here. And zero maintenance costs, a value of avoided carbon dioxide emissions of 30 euro per ton by substituting electricity generated by a coal power plant at 1 kilogram carbon dioxide per kilowatt hour. Compare it to the capital costs shown before for a medium resource, which has been at the vicinity of $2,400 per kilowatt. Thank you very much. That's it. So next lecture, we will come also to a more steady power of renewable energy, and that will be biomass power. Thank you very much.